The Yugo robotic system is Medtronic's modular robotic-assisted surgery platform, which is designed to support a wide range of minimally invasive procedures. In this presentation, we'll explore what the system is, why it exists, and how biomedical engineers fit into the bigger picture. Unlike older robotic platforms, Yugo uses modular patient-side robotic arms, meaning hospitals can configure the system differently depending on clinical needs. In practice, this offers significant flexibility in the operating room. Surgeons can adapt the system layout to almost any anatomy or procedure. The system integrates high-definition 3D imaging, advanced control software, and precise robotic articulation to help surgeons perform movements that are stable, scalable, and consistent. From an engineering perspective, Yugo represents the intersection of mechanical design, sensors, control theory, and safety critical software. As biomedical engineers, understanding these layers is key because we're responsible for maintaining its safety, its reliability, resolving faults, and ensuring the system stays safe to operate. Think of this slide deck as your high-level perspective. By the end of the deck, that you should have a clear picture of how the platform works and why it matters in modern surgical care. The stop button is normally located in here, and this would stop the system. The robotic arms, they are the center of the Yugo platform. Each arm contains multiple joints driven by high precision actuators, typically brushless DC motors paired with harmonic gear mechanisms. These provide smooth, controlled movements with very low backlash, which is essential during delicate procedures. Encoders are located inside each joint, continuously measuring the angular position, velocity, and direction, allowing the control software to monitor and adapt motion in real time. This creates a closed-loop system where the robot constantly corrects itself to stay aligned with the surgeon's input. Safety is deeply embedded. Virtual boundaries, collision avoidance routines, and force-limiting algorithms prevent the arm from moving in ways that might harm the patient. Biomedical engineers often service these arms by checking mechanical wear, verifying the encoder health, and running diagnostic movement tests. Understanding this hardware-software relationship is key to maintaining reliability. This enables the system to load correct parameters such as allowable angles, torque limits, and sterility cycle counters. Many instruments have defined usage lifespans or disposable components, and the system tracks this automatically. From a biomedical engineering perspective, understanding these life cycles restriction is very vital. So technician must know how to inspect these engagement mechanisms, verify recognition errors, and detect early signs of any misalignment or wear. This layer of the system makes sure it makes sure that the robot knows exactly what tool it's using and whether it's safe to proceed. The vision system gives the surgeon the clarity they need to operate safely. At its core, it's a 3D endoscopic camera capable of producing high resolution images with excellent depth and perception. Optical elements, lenses, filters, and illumination channels, they all work together to deliver a bright, stable view of the surgical field. And what the final output is a real-time stream that appears inside the surgeon's console. Setting up the Yugo system for surgery involves a very coordinated workflow between staff and technology. So the process always starts with transporting the modular robotic arms into the operating room and positioning them around the patient. Proper alignment of these arms and positioning them is key because it determines how comfortably the surgeon can perform the procedure. And once positioned, each arm is docked to the patient's anatomy using defined reference points. Connectivity checks ensure that the console, camera system, imaging tower, and robotic arms communicate correctly. And biomedical engineers often support the stage by verifying the power, the network health, and sensor readiness. Lastly, role of biomedical engineers. So we play a critical role in keeping the Yugo system reliable. This includes routine preventive maintenance, checking mechanical wear, inspecting connectors, testing sensors, and validating calibration. When issues arise, we must diagnose faults quickly using engineering mode, logs, and subsystem tests, which we will go over in the next following presentations about using recap and how engineers use these softwares to identify the faults in the Yugo robotic system. But the ultimate goal is ensuring that the system performs safely and consistently so surgeons can focus entirely on patient care. And understanding both the technical and clinical aspects of the platform makes biomedical engineers valuable partners in successful robotic surgery.